already. Okay, before starting the chapter 3, today I'll show you chapter 3, all of you. Before starting the chapter 3, I should show you some basic things about the matrix, determinants, and systems of equations, because these things will be required for our next chapter, in our next chapter. Okay. You will have to see the matrix and determinants and adjoint matrix in the next chapter. Okay, first of all, let's look at the matrix. I think you already know what is the matrix, right? Is it visible to you? Is it visible?
Yes, sir.
Okay. Okay, so matrix definitions and notations. First of all, this is a matrix, right? This is a simple matrix. See, M by N matrix. M by N matrix. That means M column and N rows. M by N matrix is a rectangular or square array of elements with M rows and N columns. Okay, so this is a simple matrix A. And for each substrate Aij, I is the row, and J is the column. Ij, that means first one is the row, second one is the column. First one row, second one column. If M equal to N, the matrix is said to be a square matrix. If the row and column number is same, then that matrix would be called as a square matrix. Like this. Say, let's say if we have a matrix X matrix, and you can say 1, 4, 2, 3. This is a square matrix because row 2 row 1, 2 row 2 column. That is a square matrix. That is a square matrix. Okay. That is a square matrix. 1, 4, 2, 3. Okay. I the row. Say if Aij is the element of a matrix, then I would be the row and J is the column. If M is equal to N, then the matrix is said to be a square matrix. Okay. Let's move on. Vector. If a matrix has just one row, it is called a row vector. If the matrix has just one row, then it would be called as a row vector. An example of a row vector as follows: B11, B12, B up to 1n. If a matrix has just one column, which is called a column vector. An example of a column vector follows. See, that is a row vector because the matrix has only one row. That is row vector. And if the matrix just has a one column, then it would be called as the column vector. Okay. And partition matrix. See, a matrix can be partitioned into component matrix or vectors. For example, these are the A partition matrix. A11, A12, A21, A12. Where A11 is A11, A12, A21, A22, A31, A32. A12, A13, 14, 23, 24, like this. The matrix can be partitioned into components matrix or vectors, for example. So this one, A11, this one, A11, 12, 21, 22. Okay. A11, 12, 12, 21, 22, 31, 32. And A12, A13, 13, 14, 23, 24, 33, 34. And this is A21 and this is A22. So we can partition the matrix like this. Okay, so these are the row vector, and these are the rectangular matrix. Null matrix, same. Null matrix if all elements are 0. A matrix with all elements equal to 0 is called a null matrix. Then it would be a null matrix. Aij is equal to 0 for all I and j. An example of a null matrix is as follows. This is a null matrix. Okay, so if all the elements are zeros, and diagonal matrix, this is a diagonal matrix. A square matrix with all elements of the diagonal equal to 0 is said to be a diagonal matrix. That is Aij is equal to 0 for I is not equal to j. An example of a diagonal matrix as follows. That is a diagonal matrix. So this diagonal will have values. Okay. A square matrix with all elements of the diagonal equal to 0 is said to be diagonal matrix. That means outside this diagonal, all elements will be 0. This kind of matrix is known as the diagonal matrix. Okay. Identity matrix. A diagonal matrix with all diagonal elements equal to unity is called an identity matrix. See, this is the identity matrix. If the all diagonal elements are unity, that means the 1. This Aij is equal to 1 for I equal to j, and Aij is equal to 0 for I not equal to j. That is the identity matrix. So remember, this kind of matrix are important. Okay. Now see the symmetric matrix. Symmetric matrix. A square matrix for which Aij is equal to Aji is called a symmetric matrix. An example of a symmetric matrix as follows. You see, in the symmetric matrix, say that is A1, first row, first column. A12, A13. That is A21, A22, A23, A31, 32, A33. Now here see A12, look very carefully, A12 is similar to A21 and A13 is similar to A31. And A23 is similar to A32. See, so that is symmetric matrix. That is the equation you have to remember for the symmetric matrix. Aij is equal to Aji. It is similar. In that case, that is called the symmetric matrix. Okay, symmetric matrix. Few things we have to know from this study that will be implemented in the next topic. Okay, matrix transpose. Okay, see. The transpose of a matrix A designated as A to the power T is formed by interchanging the rows and columns of A. So if you interchange the rows and columns of this matrix, then it will be a transpose matrix of A. That means column will become the row, row will become the column, whatever it is. In both angles are correct. You can use any one angle. If A is an M by N matrix with elements Aij, the transpose is an N by N matrix with elements Aij, Aji. An example follows. A, this is the A matrix. Okay, 1 7 9 2 6 3 4 8 5 -1 3 -2. Then what would be the transpose? Just make this column into the row. Then that would be transpose matrix. So remember the transpose matrix. What is the transpose matrix? Do not forget it. Okay. Now, determinant of a square matrix. So determinant, we need few matrices here in our upcoming study, upcoming topic. We need to know the transpose matrix. The transpose matrix, first one, second one, the adjoint matrix, we need to know. Adjoint matrix, how to calculate it, adjoint, and the determinant. These few things we need to know. And I think you already know the basic of matrix, and I have already discussed it here. Okay. Transpose, adjoint, determinant. Now see, what is the determinant? The determinant of a square matrix is denoted by det A. DETE, det A. Determinant det. Okay, we are use the det. DET, det A. A means the matrix. Let's say that is a matrix A. And the determinant of 2 by 2 matrix. First of all, let's talk about this is a matrix. A11, A12, A21, A22. Now see, what would be the determinant of A? See, so determinant of A, that is a determinant sign. That would be the determinant of A. Okay. Determinant of a 2 by 2 matrix. The determinant of a square matrix is denoted by det A. Remember this. That is how you calculate the determinant. A11 into A22 minus A21 into A12. Cross multiplication. Okay, so minor of element. The minor Mij of element Aij of determinant A is the determinant formed by removing the ith row and the jth column from the determinant A. As an example, consider the following determinant. Remember, if you have the multiple row, multiple column, then you have to apply a trick. What the trick? Consider the following determinant. Now consider this one. 387692514 determinant. Now we have to calculate the determinant of this one. The minor M32. So M32, what would be the M32? See, 32 means third row, second column. That means third row, second column. Third row, second column would be vanish. So you will calculate others. M32 means what? This one. This one. So what you would do? You would remove the row, this row, and this column. Remaining parts will be there. to calculate the determinant. The minor M32 is the determinant formed by removing the third row and the second column from the determinant. That means minor 32, if you want to calculate the minor 32, then you have to put these tricks. So M32 would be minus 36. Okay. And cofactor, another one. Cofactor, you would be also need this. Cofactor Cij of element Aij of determinant A is defined to be, that is the formula, cofactor formula. So if it is 3, 2, then minus 1 to the power 3 plus 2, that means the 5. So minus 1 will be remain. Mij 3, 2 minus 36. So it will be plus 30. So determinant of equation G14. So G14, say what is the G14 determinant of equation G14? As the cofactor of 2, 2, 1. Cofactor of 2, 1 would be what? So to find the cofactor of 2, 1, M21, you have to remove the second row and first column. You have to remove the second row and first column. So 8714 would be there. 8714 would be there. So 4 into 8, 32 minus 7. 32 minus 7, that is the 25, minus would be there. So it would be minus 25 cofactor. That's how you have to calculate the cofactor of an element. Okay. So we have found, we have seen how to calculate the minor of an element as well as the cofactor of an element. Okay. And evaluating the determinant of a square matrix. See, evaluating the determinant of a square matrix, how to calculate it? The formula is determinant A is equal to summation of K up to from K equal to 1 to N, Aik, Cik, where N is the number of column of A, that is the column. J is the jth row selected to expand the by minors. Cik is the cofactor of Aik. Cik is the cofactor. That is the formula. Okay. Okay, now see, for example, if A, this matrix is given, so determinant of A, by expanding by minors on the third column, we find minors in the third column, they calculate determinant of A. That means, first of all, minus 5, 6, 8, 5. So if you take this one, then you have to remove this on the third column. Okay, expanding by minors on the third column, we find minors in that third column. So if you this one, then minus 5, 6, 8, 5. This one minus 7, 1, 3, 8, 5. This one 1, 3 minus 5, 6. See, just the on the third column. If you apply the minor on the third column, then you'll get this. On the second row, if you calculate the minor on the second row, this one, then 3, 2, 5, 4, then 1, 2, 8, 4, then 1, 3, 8, 5, like this. So singular matrix, if it would be singular if the determinant equals to 0, non-singular does not equal to 0. Okay, now another one, which is the adjoint matrix. Adjoint matrix, that is another important one. So we have seen the transpose matrix, determinant matrix, and now we have to see the adjoint matrix. Then we can proceed to the next chapter. So adjoint. At the adjoint of a square matrix A, written at edge A, ADJA, is the matrix formed from the transpose of the matrix A. That is the transpose of the matrix. Cofactor. the matrix say after all elements have been replaced by their cofactors. So all elements need to be replaced by their cofactors. Now consider the following matrix. So this matrix you consider. So you have to calculate the cofactor. So first one, for the first one, what would be the cofactor? For this one, 4587. Say for the second one, for this, -1567. Cofactor. This would be the cofactor. 1 1 positive, and 1 2 negative. It would be negative, and 1 3 positive. So positive. So like this, sign would be changed. So cofactor. You have to calculate the cofactor of this matrix. Then you will get the adjoint matrix. Okay. So remember this adjoint of matrix. Okay. And rank of matrix. The rank of matrix A is equals to the number of linearly independent rows or columns. Okay, these things will not be required because I think you already know those things. Cramer's rule. So you have to, I think you know the Cramer's rule already. We have discussed it previous. See solution by Cramer's rule. Okay, whatever. Now we will move to the our chapter. Okay. That is our chapter 3. Modeling in the time domain. Modeling in the time domain. That is chapter 3. Okay. Modeling in the time domain. Okay, so before proceeding the chapter, tell me what have you understood so far? Shobhan. Shobhan. শোভন কোথায়? এই ছেলেটাকে যখন খুঁজি তখন পাই না। মিঠুন।
জি স্যার।
হ্যাঁ বলো, তুমি অ্যাডজয়েন্ট ম্যাট্রিক্স বলতে কি বুঝছো?
হ্যাঁ, এগুলো তো সব মাথার উপর দিয়ে গেছে।
মাথার উপর দিয়ে তুমি ইঞ্জিনিয়ারিং পড়তেছো, তোমাকে বুঝতে হবে।
এগুলো দেখতে হবে, বারবার দেখতে হবে।
দিবা। দিবা। দিবা তুমি শুনতেছো?
জি স্যার, আমি শুনতে পাচ্ছি।
আচ্ছা, তুমি কি বুঝছো এই যে ম্যাট্রিক্সের এগুলাকে দেখছিলা?
জি স্যার, এগুলো ইন্টারমিডিয়েটে করছিলাম।
হ্যাঁ, এগুলা এখন লাগবে।
হ্যাঁ স্যার।
ট্রান্সপোজ ম্যাট্রিক্স কি বুঝছো?
স্যার মানে মূল ম্যাট্রিক্সের যেটা মানে রেজাল্ট হবে ওটাকে স্যার ইনভার্স করতে হবে, ওইটাই স্যার ট্রান্সফর্ম।
হ্যাঁ, কলাম হবে রো, রো হবে কলাম।
কলাম, হ্যাঁ।
ওকে, গুড। শোভন কোথায়? শোভন 18, খবর নাই। 16, 16 কে? 16 তো ক্লাস করে না দেখি।
না স্যার, ও ক্লাস করে না।
ক্লাস করে না কেন?
স্যার বলতে পারি না, কোনো ক্লাসই ও আসে না।
আচ্ছা, এখানে তো আমি আসলে এর আগের সেমিস্টার in the previous course I have not checked the attendance very accurately because I already gave the marks, attendance marks, almost in average mark I gave to you, But I think from this semester, I have to check your attendance very carefully. Okay. Because it is
Okay,
not
sir.
fair. It is not
Okay,
fair
sir.
that
Okay, sir.
some guy, they will not attend the class and they will get the marks. And on the other hand, some guys do class regularly. And same, they are not the same. But previously, I considering the all situation, the COVID situation, I gave the marks. But I think it is better to give the mark accurately in case of the attendance.
Okay, sir.
Okay.
Okay.
So tell your friends who are absent all the time.
Okay, sir. Shall.
And also, I'm not happy with the Shobhan. Shobhan is not responding. Roll 18. Roll
I will
16.
be
I
sir.
do not know who is he. Roll 16 is not attending the class. And what about the roll 8? He is also culprit. Roll 8.
আসসালামু আলাইকুম স্যার স্যার আমি আসি স্যার
আজ থাকলে রেসপন্স করো না কেন? তোমাকে রেসপন্স করতে হবে, কারণ অনলাইন মানে যে তুমি ঢুকে আবার ঘুমায় যাবা সেটা না, তোমাকে অ্যাটেন্ডেন্স থাকতে হবে।
জি স্যার থাকবো স্যার।
কারণ অনলাইন ক্লাস ধরো আমি কয়েকটি ইউনিভার্সিটি দেখছি কিরকম হয় অনলাইন ক্লাস, সেই হিসাবে তো আমাদের অনেক ছাড় দেওয়া হয়। যেমন আমি নিজে বুয়েটের ক্লাস করছি, বুয়েটে আমি দেখছি যে ওখানে কোনো ইয়ে নাই, প্রতিটা ক্লাসের শেষে ক্লাস পারফরমেন্সের একটা ইয়ে থাকে, কিছু কোশ্চেন থাকে, তোমাদেরও সেভাবে দিতে হবে আর কি। হ্যাঁ শোভন বলো, তুমি ইয়ে কি বুঝছো, ডিটারমিনেন্ট বলতে কি বুঝছো?
স্যার এগুলো স্যার একটু স্যার আমাকে স্যার দেখতে হবে স্যার, আরো 2-3 বার দেখলে তারপর স্যার বলতে পারবো।
আচ্ছা ওকে, হোয়াট অ্যাবাউট দ্য রোল 10? ইসমাইল, Ismail, you there? Mr. Ismail, roll 10.
Yes, sir.
Okay, so tell me what is the cofactor?
Hello.
Cofactor, what is the cofactor? Cofactor?
Yes, sir.
Can you tell me?
The percentage of common area within the rest of room.
Okay. Okay, at least you have tried. Okay, thank you.
Okay, okay, sir.
Okay, so let's move on to the next chapter, which is the modeling the time domain, which is chapter 3. And in this chapter, after completing this chapter, we will move on to chapter 7, 7, 8. Mainly, we have to complete the 7, 8, 10. 3 more chapters, excluding this one.
Okay, sir.
Okay, excluding this one, we have to complete the 3 more chapters. I think it is possible. And in the final assessment, you will get the question from all of the chapters. The weight of the final assessment would be 20 marks. Okay, 20 marks. But I'll give you the 40 marks questions. Okay, I'll give you the 40 marks question. It would be open book exam. Okay, it would be open book, and Viva would be 30 marks. Okay, so Viva, I'll take the Viva later after completing the assessment. Okay, we'll plan it later. Okay, let's move on.
Okay, sir.
Okay, the state space representation outline of this chapter is a state space representation. First of all, we'll see the state space, then we'll see the converting from transfer function to state space, then converting from state space to transfer function. In this case, third portion, converting from state space to transfer function, in this case, we need to know the adjoint matrix as well the determinant matrix. That's why I have shown those things to you. Okay. So let's move on. State space representation. Okay. So if we have a feedback control system, we have two approaches to analysis and design of this system. Two approach. One approach is classical or frequency domain technique. Another approach is time domain technique. So we have studied the frequency domain technique in the chapter 2. In the chapter 2, we have studied the frequency domain technique. Okay. The approach is based on converting a system's differential equation to a transfer function, thus generating a mathematical model of the system that algebraically relates a representation of the output to a representation of the input. You understand? So first of all, what we did, we have done the conversion of the differential equation to the transfer function. Then we calculated. And replacing a differential equation with an algebraic equation not only simplifies the representation of individual subsystems, but also simplifies modeling interconnected subsystems. Okay. So primary advantages of this is it can be applied only to linear time invariant systems or systems that can be approximated as such. The state space approach, also referred to as the modern or time domain approach, is a unified method for modeling, analyzing, and designing a wide range of systems. So a state space is the new one, comparatively new if we compare it with the other one. It is known as the modern or time domain approach. This state space approach is known as the modern or time domain approach. It is a unified method for modeling, analyzing, and designing a wide range of systems. That is a unified method. Okay. So that is important one. Okay. So we have to look at the state space approach. So far, we have seen the transfer function approach. That means the classical frequency domain approach. Okay. So see, the state space approach can be it can represent the nonlinear system that have a backlash, saturation, and dead zone. Also, it can handle conveniently systems with non-zero initial conditions and time varying systems. That means the missiles with varying fuel levels or lift in an aircraft flying through a wide range of altitude can be represented in state space. Many systems do not have just a single input and a single output. See, many systems do not have only just a single input and single output. Multiple input, multiple output systems, such as a vehicle with input direction, an input velocity, yielding an output direction and an output velocity, can be compactly represented in state space with a model similar in form and complexity to that used for single input, single output systems. Okay, that time domain approach can be used to represent systems with a digital computer in the loop or to model systems for digital simulation. Okay, with a simulated system, system response can be obtained for changes in system parameters. Okay. Okay, now let's move on the state space representation. Okay. Now see, a system is represented in state space by the following equations. For getting the state space equation, we have to consider these two. Okay. First equation, x dot is equal to x plus bu. X dot means the derivative. Dot means, what does it mean? Dot means, say, if we write dx by dt, then we can write like this, x dot. That means derivative of x is x dot. If we have double derivative, then x double dot. If we have triple derivative u, then x triple dot. Like this. Dot comes from the derivative d by dt. D by dt is actually the dot. Okay, is it clear to you, Mithun?
Yes, sir.
D by dt represent the derivative. If you have the x, and then if you differentiate it with respect to time or whatever, then d by dt is equal to dx is equal to x dot. Okay, that is the x dot. Okay, so we have the x dot is equal to x plus du, y is equal to cx plus du. Where x is the state vector, x dot is the derivative of the state vector with respect to time. And y is the output vector, where u is the input or control vector, a is the system matrix, b is the input matrix, c is the output matrix, and d is the feed forward matrix. Okay, so these are the equations, these are the matrices we have to check out in our problem. Okay, first problem. Representing an electrical network. So this is the electrical network. Given the electrical network figure 3.5, find a state space representation if the output is the current through the resistor. If the output is the current through the resistor. Electrical network for representation in state space. Okay. Say, this is a network. The first of all, label all of the branch currents in the network. This includes IL. So branch currents, this one branch, this another branch, this is another branch. So first label all the branch currents. IL, branch current IL, branch current IL, branch current IC. Okay. Now select the state variables by writing the derivative equation for all energy storage elements. That is the inductor and the capacitor. So energy storage element. So what are the energy storage element? Inductor and the capacitor. For them, we have to write the derivative equation. dVc by dt is equal to IC. LdIL by dt is equal to VL. Okay. Now, apply network theory such as Kirchhoff's voltage and current laws to obtain IC and VL in terms of the state variables. So we are taking the equation 3.22 and 3.23. Choose the state variables as the quantities that are differentiated. That means Vc and IL would be our state variable because we have differentiated it all. So those will be our state variables. We see that the state space representation is complete if the right hand sides of the equation and can be written as the linear combination. So linear combinations of this variable. Okay, since IC and VL are not state variables, our next step is to express IC and VL as linear combination of the state variables, VC and IL. Okay, so and the input VT. Let's say, so let's apply the Kirchhoff's current law. IC is equal to minus IR plus IL. So IC is equal to what? Actually, IL is equal to IR plus IC. So IC is equal to IL minus IR. See here, let me write. Here, see very carefully. IL is equal to IR plus IC. Then what I can write, if I want to calculate the IC, then IC would be equal to minus IR plus IL, right? It is IC equal to minus IL plus IL. That is the equation by applying the Kirchhoff's current law, KCL. This one plus this one is equal to this one plus this one. Now, what would be the IC? IC is equal to the negative of this, the difference of this. Okay, so instead of IR, we can write what? 1 by R into VC plus IR. I can write like this. And IC, instead of IC, around the outer loop, VL is equal to minus VC plus VT. VL is equal to what? That means this one, this VL minus VC plus VT. Minus VC plus VT. So here we have found the IC and VL. The equation of linear equation of VL and IC. Now put these two in the equation 3.22 and 3.23. Put these two in the equation, then again cross multiplication divided by C and divided by L, then we will get like this. The output equation, that means the IR, since the output is the IR, 1 by R into VC. Now from this we will write the equation. From this we will write the state space equation. So see VC d by dt into VC, that means VC dot d by dt into IL, that means IL dot. So for this one, minus 1 over RC, 1 by C minus 1 by L, and plus 1 by L. It would be 0, I think. Okay. See, here the VC term and the IL term. So here IL term is 0, so it would be 0, VCIL. And for the VT, first one 0, second one 1 by L. Okay. And for the IR, 1 by R and 0, VC and IL. VC term is there, but IL term is 0. Dot indicates differentiation with respect to time. See, but the dot indicates the differentiation with respect to time. Oh, it is a translational mechanical system. Similar thing would have would apply for the translational mechanical system. Same thing would happen. Find the state equations for the translational mechanical system shown in figure. This figure is given frictionless. Right, at first there will be two equations. Two equations are there. At first write the equations, then take the state variable. Now take the state variable x1. Now d square x1 dt square is equal to dv1 dt, and ds a double derivative dv2 dt. x1, v1, x2 and v2 as a state variable. dv1 dt and dv2 dt. So first of all, add dx1 and dt to the complete set equation. Now dx1 dt v1, dv1 dt is equal to what? Just do the calculation. So just differentiate it, then you will get this one. And dx2 dt v2 and differentiate it, then you will get this one. Now from this we can write the matrix. So x1 dot plus v1, others are 0, v1 dot this one, this one, this one, others are 0, and v2 term is 1, v dot 2, these will be the equations. Okay, ft is here, so ft is separate. Okay. Okay, so what would be the output is xt. So for the xt, so what would be the output? Okay, so they have shown this one. Since almost similar thing is given here, you can check. And another one is given. Okay. Now the second part, converting from transfer function to the state space. So if you have the transfer function and how to convert it to the state space. Okay. See. Okay. We'll go to the problem very quickly. Find the state space representation in phase variable form for the transfer function shown in figure 3.10. This one. This transfer function is given. From these, you have to calculate the state space variable or state space representation from this one. How to do it? First of all, we know what? CS by RS. CS by RS is equal to this one. Now cross multiplied it. Cross multiplication. Now see, the corresponding differential equation is found by taking inverse Laplace transform. So to get the differential equation, just inverse it. Inverse this one. S cube means triple dot. S square means double dot. S means single dot. Like this way. Cross multiplying years. (24). The corresponding differential equation CS cube 9s square plus 26s plus 24. Just put those values. Okay. C triple dot, C double dot, C single dot, C no dot. Okay, 24. These are the things. Then now you have to select the state variables. So which are the differentiators? So C dot, C double dot, C triple dot. Let's see, x1 is equal to C, x2 is equal to C dot, and x3 is equal to C double dot. Choosing the state variables as successive derivatives. x1 C, x2 C dot, x3 C double dot. And now differentiate both. x1, differentiate x1 means x1 dot, which is equal to x2. Okay. And x2 dot, which is equal to x3. Like this equation will come. Then y is equal to c is equal to x1. So just put this one into vector matrix form. This one. Now see x1 dot. X1 dot, that means C dot. C dot means x2. Have you got it from here? If you differentiate it, then these will become like this. X1 dot, which is equal to C dot. So C dot is equal to what? X2. Again, X2 dot. X2 dot means C double dot. C double dot means what? X3. And X3 dot. X3 dot means C triple dot, which is equal to C triple dot. How you'd get it? You'd get it in the previous one. C triple dot is equal to 24R minus 9 C double dot minus 26 C dot minus 24 C. That thing applied here. Same thing. And Y is equal to C is equal to X1. Now put those values here, then you will get the static space representation. And if you have the polynomial in the numerator, this one denominator, this one numerator. So if you have the polynomial, then how to do it? If you have the polynomial, then as usual, first thing first, solve it. Then you have to check the second one. And similarly, we have to convert the state space to a transfer function. Okay, so I think this from the I am stopping today because many things have been discussed. So from the next class, in the next class, I'll see the example 3.5 as well as this converting, because this thing will take time. 3.6, I have to explain thoroughly.
Okay, sir.
So it will take time.
Sure.
So inshallah, I'm closing here, because you need to, since it is mathematical thing, so you have to understand very clearly. Okay. Okay, do you have any questions?
No, sir, maybe.
Okay, just a minute. I have to take the attendance.